Tonight, we're going to look at the largest planet in our solar system and ask whether its 318 Earth masses are the reason Earth is still here. Jupiter hangs beyond the asteroid belt, bright enough to see without a telescope, turning once in less than 10 hours and carrying more material than all the other planets combined. Its gravity reaches across millions of miles without forming a visible boundary. Comets pass through that influence. Asteroids respond to it. Other planets exchange small, persistent pulls with it over billions of years. This has produced one of astronomy's most durable stories. Jupiter is often pictured as a guard, stationed outside the terrestrial planets, intercepting objects that might otherwise reach Earth. The image is simple. The dynamics are not. A gravitational encounter can remove a small body from the solar system, but it can also redirect that body toward the sun. A resonance can preserve an orbit for ages, or gradually stretch it until it crosses a planet's path. Did Jupiter protect our world, endanger it, or help build the only version of the solar system in which Earth could form? By the end of tonight, you're going to understand exactly how Jupiter shaped the young planetary disk, how it changes the traffic of asteroids and different families of comets, and why scientists cannot reduce those effects to the word shield. The answer reaches back before Earth had oceans, before the asteroid belt acquired its present gaps, and before the giant planets arrived at the orbits they occupy now. Before we get started, if you love exploring Jupiter and the history of the solar system as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with the number that gives the story its scale. Jupiter has 318 Earth masses. That mass does not form a wall. It forms a moving gravitational landscape, circling the sun once every 4,333 Earth days. Everything that approaches it enters a negotiation among speed, direction, distance, and time. Some objects leave that negotiation farther from Earth, some leave it closer, and the planet itself preserves no record of the paths that never happened. The first distinction is between Earth existing and Earth remaining unstruck. Those are not the same claim. Earth formed about 4.5 billion years ago through collisions and accretion. Its present orbit, mass, water inventory, moon, atmosphere, and biological history emerged from that long sequence. To say Jupiter is the reason Earth still exists could mean that Jupiter helped a roughly Earth mass planet form here. It could mean that Jupiter later reduced catastrophic impacts. Or it could mean both. Each meaning requires different evidence. Planet formation models examine the first few million to hundreds of millions of years, when gas, dust, planetesimals, and planetary embryos exchange material. Impact studies examine later populations of asteroids and comets, often by changing Jupiter's mass or orbit in computer simulations. Geological and biological records ask what impacts actually did after Earth formed. One result cannot automatically answer all three questions. The meanings also use different thresholds. A shift in the number of small impacts may matter to crater production without threatening a biosphere. A change in the early disk mass can alter which planets form without saying anything about later comet traffic. A reduction in one comet family can be genuine while remaining too small to determine the fate of Earth. Evidence must be matched to the claim it can actually carry. There is also a problem hidden inside the word without. Removing Jupiter from a simulation is not like lifting one ball from a finished model of the solar system. Jupiter formed early. Its growing gravity may have separated reservoirs of material, opened gaps, driven migration, and altered the growth of Saturn and the smaller planets. A system that never formed Jupiter would begin differently. By the time an Earth analog appeared, if one appeared at all, the entire map could have changed. That makes the title a counterfactual. Science can compare modeled systems with different giant planets. It can measure the present trajectories of real objects. It can infer past events from meteorites, craters, and orbital distributions. It cannot observe a second solar system identical to ours except for one missing Jupiter. The strongest answer must therefore distinguish what is measured from what is reconstructed. The measured facts begin with Jupiter itself. The modeled facts begin with alternate histories. The uncertain part lies between them. So the standard for this journey is careful. Whenever a simulation produces an effect, it will be described as a result within that model. Whenever an observation shows Jupiter capturing, scattering, or being struck by an object, it will be treated as one real trajectory, not proof of every unseen alternative. The title asks for a single reason. The evidence offers a network of causes. Jupiter's physical scale explains why it dominates every gravitational discussion about the planets. Its mean radius is 69,911 kilometers, about 11 times Earth's radius. Its volume could contain roughly 1,000 Earths, though its mass is only 318 Earth masses, because Jupiter is made mostly of hydrogen and helium rather than rock and metal. It is large without being uniformly dense. The planet travels at an average distance of 778 million kilometers from the Sun, or 5.2 astronomical units. Sunlight takes about 43 minutes to reach it. Jupiter completes one orbit in nearly 12 Earth years, yet its day lasts only about 9.9 hours. That rapid rotation broadens the equator and helps organize the alternating cloud bands visible through small telescopes. None of those dimensions by itself creates a shield. The important quantity for nearby small bodies is the combination of mass and encounter geometry. Jupiter's escape speed is far greater than Earth's. Far outside the atmosphere, its gravity can still bend an object's heliocentric orbit during a close approach. A small body may gain energy relative to the Sun, while Jupiter loses an imperceptibly small amount, or it may lose energy while Jupiter gains the same tiny amount. The visible planet and the dynamical planet are therefore different scales. The striped disk ends at the atmosphere, but the orbital influence has no crisp painted edge. The 4 large Galilean moons occupy only the inner part of a much larger satellite system. Beyond them, irregular moons trace distant, inclined orbits. Farther still, solar gravity dominates again, yet Jupiter remains strong enough to alter objects that approach on heliocentric paths. This is the natural version of the gravity assist used by spacecraft. Voyager 1 gained speed through its 1979 Jupiter encounter. Galileo used flybys of Venus and Earth on the way outward. Lucy is using repeated Earth encounters to reach the Trojan asteroids. Gravity does not know whether the traveler is a machine or a comet. It responds to mass, position, and velocity. Jupiter has more than twice the combined planetary mass outside the Sun's own mass. Saturn is substantial at about 95 Earth masses, but Jupiter remains the principal planetary term in many small body orbits. Over one encounter, the deflection may be obvious. Across thousands of distant passages, the influence can accumulate through resonance. Keep the opening number nearby. Jupiter has 318 Earth masses. That is enough to rearrange populations, but not enough to choose a moral role. The same mass that can fling a comet outward can place another object on a shorter period orbit. Size establishes power. It does not establish protection. The shield metaphor fails first because gravity has no front surface. A physical shield absorbs or blocks something approaching from one side. Jupiter circles the Sun while comets and asteroids arrive on orbits with many inclinations, speeds, and directions. Some never come close to the planet. Some cross its path repeatedly. Some interact through resonances from millions of kilometers away. Imagine an icy body falling inward from the outer solar system. As it approaches Jupiter from behind in the planet's orbit, Jupiter may pull it forward and increase its heliocentric energy. The object can move onto a wider orbit or escape entirely. Approaching with a different geometry, it can leave with less heliocentric energy and a smaller orbit. Both outcomes follow the same gravitational law. The planet also moves during the encounter. A static Jupiter would bend a trajectory, but could not exchange orbital energy in the same way. The moving planet acts as an enormous reservoir of momentum. A comet's gain or loss is balanced by a change in Jupiter's motion too small to measure in ordinary terms, because Jupiter is vastly more massive than the comet. Astronomers describe the incoming and outgoing paths with conic sections. An object bound to the sun follows an ellipse. An object with exactly the escape energy would follow a parabola in the ideal two-body limit. Add enough energy and the path becomes hyperbolic. Jupiter can move a small body from one category to another, but the outcome is measured relative to the sun, not Jupiter alone. Three bodies are participating even before Saturn or the terrestrial planets are included. Distance matters sharply. Gravitational force weakens with the square of separation, so a close approach can dominate years of weaker influence. Yet close is a relative word around Jupiter. The planet's hill sphere, the region where its gravity dominates over the sun for satellite motion, extends tens of millions of kilometers. Its moons occupy only part of that broad domain. Time adds another layer. An asteroid in a mean motion resonance does not need to pass near Jupiter today. Repeated gravitational nudges can occur at similar places in the orbit. Over long intervals, they may alter eccentricity, the measure of how stretched an orbit is. A nearly circular path can become elongated enough to cross Mars or Earth. Other resonances do the opposite and protect stable populations. The Trojan asteroids share Jupiter's orbit near two gravitationally stable regions. The Hilda asteroids occupy a 3-to-2 resonance, completing 3 orbits for every 2 of Jupiter's. These objects are organized by the same planet that helps empty the Kirkwood gaps. Jupiter is therefore not a wall at 5.2 astronomical units. It is a moving set of pathways. Some are exits, some are entrances, some are long-term storage. The role changes with the traveler. The present solar system encourages a misleading picture of formation. Today, the planets occupy broad, mostly separated lanes. The early solar system was a disk of gas and solids surrounding the young sun. Dust grains collided and adhered. Larger aggregates became planetesimals. Some grew into embryos, and a few acquired enough gas to become giant planets before the disk dispersed. The sequence unfolded quickly by planetary standards. The gaseous disk survived only a few million years. Jupiter had to gain a large atmosphere while that gas remained available. Rocky planets continued assembling for tens of millions of years after the giant planets had become dynamically important. The outer system became powerful before the inner system was finished. Position was not fixed. A planet embedded in gas exchanges angular momentum with the disk. Depending on the planet's mass and the structure of the gas, that exchange can drive migration. Planetesimals scattered inward or outward can also carry angular momentum and shift a planet's orbit. The neat distances measured today are endpoints, not necessarily birth addresses. This distinction matters for Earth. A growing Jupiter could alter the supply of solid material reaching the terrestrial region. Its resonances could concentrate or disperse planetesimals. Its movement could truncate one part of the disk and mix another. Saturn's growth could then change Jupiter's migration. The emerging planets were coupled through the disk before they were coupled through empty space. No astronomer watched this happen. The evidence remains in indirect records. The ages and isotopic compositions of meteorites, the masses and orbits of planets, the chemical mixture of the asteroid belt, and the populations beyond Neptune. Models are judged by how many of those records they reproduce without requiring impossible conditions. Several models can explain parts of the same evidence. The Grand Tack focuses on gas-driven migration of Jupiter and Saturn during the disk era. The NICE model and its descendants focus on later migration and instability among the giant planets interacting with a planetesimal disk. Neither name describes a video recovered from the past. Each describes a family of calculations. The shield story begins late, with a completed Earth and incoming debris. The architectural story begins here, while there is no completed Earth to shield. Jupiter's first influence may have been less like guarding a house and more like changing the supply of wood, stone, and space from which the house could be built. Meteorites provide one of the most precise clocks for Jupiter's early growth. Certain meteorite groups carry different isotopic signatures, indicating that their source materials belong to two reservoirs in the young solar system. Those reservoirs remain separated for a substantial interval, even though gas and small solids were moving through the disk. In 2017, Thomas Kruger and colleagues used tungsten and molybdenum isotope chronologies to infer that Jupiter created the barrier. Their analysis placed the growth of Jupiter's solid core at about 20 Earth masses within the first million years after solar system formation. The planet then grew to roughly 50 Earth masses by 3 to 4 million years before acquiring most of its present hydrogen and helium envelope. The inference joins laboratory measurements to disk physics. Meteorites do not contain a fossil image of Jupiter. They contain isotopic patterns and formation ages. Researchers compare those patterns with mechanisms capable of keeping two source regions apart. A growing giant is a strong explanation because it can alter the movement of solids through the gas disk. Future models can refine how complete the separation was, but they must still account for the observed division. The exact growth history remains an inference, but the timing makes one point clear. Jupiter became dynamically significant very early. Earth was not yet a finished planet. Mars was not yet the small world we know. The asteroid belt was not a stable collection between established borders. Material on the two sides of Jupiter's orbit experienced different histories. A 20 Earth mass core does not need to occupy the full present orbit to affect drifting pebbles and planetesimals. It can open structures in the gas, alter pressure gradients, and scatter larger bodies. As gas accretes, the influence grows. By 50 Earth masses, the young Jupiter is already more massive than Neptune and approaching Saturn's present mass. Then the planet continues toward 318 Earth masses. Its envelope swells while the disk still contains gas. The gravitational barrier is not perfectly sealed. Later work emphasizes that some material crosses and that mixing occurs. But the isotopic division suggests that Jupiter helped maintain two chemically distinct neighborhoods long enough for their differences to survive in meteorites. This early separation complicates any attempt to remove Jupiter from history. Without the growing giant, solids might drift and mix differently. The cores of terrestrial planets might accrete different proportions of dry and water-bearing material. The timing of embryo growth might change. Even Saturn's subsequent migration would unfold in another disk. Jupiter's oldest known effect is therefore not a documented interception of a comet bound for Earth. It is a reorganization inferred from stones that formed before Earth was complete. The evidence begins with architecture, not defense. A barrier in a disk is not an absolute partition. Gas can cross gaps. Small dust can be carried with it. larger bodies can be scattered around the planet, and migration can move the boundary itself. The two meteorite reservoirs remain distinct enough to record separation, yet the present solar system also contains evidence of broad mixing. The asteroid belt is the clearest example. Asteroids closer to the Sun tend to include brighter, relatively dry silicate-rich types. Darker, more carbon-rich bodies are more common farther out. The division is not clean. Different compositions overlap across the belt, and several formation models explain that mixture by moving bodies inward and outward during the giant planet's growth. Jupiter can produce both separation and exchange because those processes occur at different scales and times. A pressure structure in the gas may slow the inward drift of small particles. A planetesimal passing near the planet may be scattered across the boundary in a single encounter. A migrating resonance can carry a population through regions that were previously disconnected. The young sun adds heat, radiation, and a changing gas environment. Saturn grows farther out. Planetary embryos inside the snowline collide. Beyond the snowline, water and other volatile compounds condense more readily into solids. There is no single conveyor belt labeled dry or wet. There are overlapping flows. This is why the phrase Jupiter delivered Earth's water needs restraint. Jupiter's formation and migration may have assisted the inward transport of water-bearing material. Some simulations reproduce Earth-like water inventories from primitive bodies scattered out of the outer belt or beyond. But Earth also acquired and lost material through many impacts, including the giant collision associated with the Moon's formation. The source fractions remain an active research problem. Chemical fingerprints provide constraints without naming one root. Different classes of meteorites preserve characteristic isotopic ratios. Earth's water and volatile elements can be compared with those records, but later processing complicates the match. Mantle exchange, atmospheric escape, core formation, and impacts modify inventories. A dynamical model may deliver the right amount from the wrong reservoir, or the right reservoir at a stage when too little is retained. The important conclusion is narrower. Jupiter altered access. It changed which reservoirs communicated, when they communicated, and how efficiently bodies crossed from one region to another. In one circumstance, it behaved like a barrier. In another, it behaved like a mixer. That dual role survives today. Jupiter stores Trojan asteroids in stable resonance while helping clear other resonant locations. It can shorten the life of a comet by ejecting it, while first steering it through the inner solar system. A single label will continue to fail because the planet does not perform a single dynamical operation. One influential reconstruction of Jupiter's early movement is called the Grand Tack. The name comes from sailing. A boat changes direction relative to the wind by tacking. In this model, Jupiter migrates inward through the gas disk and later reverses direction after Saturn catches it, and the two planets enter a resonant relationship. Kevin Walsh and colleagues published the classic version in 2011. Their simulations began with Jupiter moving sunward through a disk of planetesimals. The planet's inward passage scattered material, emptied regions, and compressed the solids available to build the terrestrial planets. In successful runs, Jupiter turned around near 1.5 astronomical units, not far beyond the present orbit of Mars. Migration through gas does not resemble a planet cutting a clean trench through stationary gravel. The gas itself orbits, pressure changes across the disk, and the planet launches spiral density waves. Material can be shepherded ahead of a resonance, scattered during a close encounter, or carried with evolving gas structures. The final edge of the terrestrial disk emerges from many interactions rather than one sweep of Jupiter's physical diameter. That would place the giant planet far inside its current distance of 5.2 astronomical units. It would not enter Earth's present orbit at 1 astronomical unit, but it would approach the region from which Mars and the outer portion of Earth's building material emerged. The gravitational landscape of the inner disk would change profoundly. The model addresses an old problem. Straightforward terrestrial planet simulations often produce a Mars analog that is too massive. The real Mars has only about 11% of Earth's mass. If Jupiter's inward migration truncated the disk near 1 astronomical unit, the region around Mars would contain less material. Earth and Venus could grow large inside the edge, while Mars remained small near it. The tack is not established history. It depends on how Jupiter and Saturn interact with gas, how quickly Saturn grows, and how the disk evolves. Later models offer other routes to a small Mars and the asteroid belt structure. The value of the Grand Tack lies in showing that one coherent migration can reproduce several otherwise puzzling features. It also changes the title. If this model resembles the real early solar system, Jupiter did not merely wait at the outer boundary and block incoming comets. It moved inward, disrupted the planet-forming disk, and helped determine how much material remained available at different distances. That is not protection in the ordinary sense. It is construction by removal. A smaller Mars, a truncated inner disk, and a mixed asteroid belt become related consequences of one hypothetical journey. Earth exists inside that rearranged outcome, not behind it. The outward leg of the Grand Tack requires Saturn. A lone giant embedded in a gas disk tends to continue migrating according to the torques acting on it. In the model, Saturn forms later and farther from the Sun, migrates inward more rapidly, and approaches Jupiter. The planets become locked in a 3-to-2 mean motion resonance. In that configuration, Saturn completes 2 orbits for every 3 completed by Jupiter. Their combined interaction with the disk changes the balance of torques. The pair reverses direction and migrates outward. Jupiter returns toward roughly its present neighborhood, while Saturn moves with it toward the outer system. The turnaround matters because an inward-moving Jupiter that never stopped could destroy or scatter much of the terrestrial disk. The model needs the tack to occur at the right stage and distance. Too early, too late, too near, or too far changes the masses and orbital spacing of the planets that follow. The architecture depends on timing. During the outward movement, Jupiter and Saturn scatter new populations through the asteroid region. Some bodies originally located closer to the Sun are implanted outward. Other bodies from beyond the giant planets are implanted inward. The belt left behind is low in total mass, but mixed in composition, resembling broad features of the observed belt. Mars forms near the truncated edge. Earth and Venus continue assembling inside it for tens of millions of years. The giant planets complete their gas era journey much earlier. This sequence places Jupiter in the role of a sculptor whose tool is migration, but even that metaphor must remain conditional. The Grand Tack is one reconstruction among several. The model does not prove that a planet named Earth required this exact route. It shows that Jupiter and Saturn can create initial conditions from which plausible analogs of the terrestrial planets emerge. Another starting disk or another instability can produce different successful outcomes. Still, the idea changes what it means to ask whether Jupiter saved Earth. The earliest relevant action might have been a partnership between 2 giant planets, not a collision between Jupiter and a threatening comet. The decisive event, if it occurred, was a turn in a gas disk before Earth had a final surface to protect. Between Mars and Jupiter lies a belt whose total mass is far smaller than Earth's moon. Popular diagrams make it look crowded because asteroid sizes are exaggerated and distances are compressed. In reality, spacecraft cross the belt without weaving through a stone field. Its emptiness is part of the evidence. A simple planet formation disk might be expected to build a planet in this region. Jupiter's gravity helps explain why that did not happen. Resonant perturbations raise orbital eccentricities and relative velocities. Collisions become erosive rather than gently accretional. Material is scattered inward, outward, or out of the solar system. The belt loses most of what it once contained. The largest surviving body, Ceres, is a dwarf planet, while Vesta preserves a differentiated interior and an enormous impact basin. Their survival shows that growth did occur, but the process stopped short of assembling an Earth-mass planet. Countless smaller fragments record later collisions. Jupiter's role is visible in the large-scale orbital structure, while the detailed family tree of the belt also carries the work of impacts, thermal drift, and secular perturbations. Yet the exact history is debated. The Grand Tack begins with material in the belt region, removes much of it, then repopulates the zone from distinct reservoirs. Other models propose that the primordial belt was nearly empty and was filled from both inner and outer sources. In either family, Jupiter is central because its resonances and encounters govern what can remain. The surviving belt retains gradients. S-type asteroids, commonly associated with silicate-rich material, dominate much of the inner belt. Carbon-rich C-types are more prevalent farther out, but the overlap prevents a simple two-color map. Families created by collisions add another pattern. Resonances cut through all of them. This matters for Earth because the belt is not only an archive, it is also a source region for near-Earth asteroids. Thermal effects can slowly change a small asteroid's orbit until it enters a resonance. Jupiter and the terrestrial planets can then alter its eccentricity and inclination. A body stored safely for billions of years may begin a comparatively short journey toward planet-crossing space. The same Jupiter that helped prevent a planet from growing in the belt did not remove every asteroid. It created a depleted, structured reservoir with escape routes. Some routes lead away from Earth. Some lead toward it. The belt therefore resists the Guardian story. It is neither a pile of projectiles waiting for Jupiter to catch, nor a harmless collection kept permanently outside. It is a population continuously edited by collisions, sunlight, resonances, and planetary encounters. Jupiter is the strongest distant editor, but editing includes deletion and redirection. Earth's surface oceans contain only a small fraction of the planet's total mass, yet their origin is one of the deepest questions in planet formation. The inner disk was hot enough that the building materials near Earth's orbit were relatively depleted in volatile compounds. Water-rich bodies formed more readily farther from the sun. Some material had to cross the early system's chemical and dynamical boundaries. Jupiter could affect that crossing in several ways. Its growing mass could block the inward drift of some solids. Its encounters could scatter larger water-bearing planetesimals inward. If it migrated, resonances and close approaches could move entire populations across the asteroid region. The direction and efficiency depend on size, timing, and disk conditions. Simulations within the Grand Tack framework have delivered primitive, water-bearing planetesimals into the terrestrial region. In some runs, the resulting planets acquire water mass fractions comparable to estimates for Earth. A 2023 study of Jupiter's growth and migration also found substantial inward transport, while emphasizing dependence on assumed initial distributions and what happened to water during later collisions and core formation. Those results do not mean Jupiter filled the oceans. They show that Jupiter can open routes for material, whose isotopic and chemical properties resemble parts of Earth's volatile inventory. Other sources and processes contribute. Some water may have been incorporated earlier than once assumed. Some is stored in the mantle. Some was lost during giant impacts and atmospheric escape. The distinction between delivery and survival is essential. An impact by a water-bearing body can add useful volatiles. A larger impact can remove atmosphere or melt crust. Planet formation itself depends on impacts. A collision-free Earth would never assemble. The biological meaning of bombardment changes with energy, frequency, timing, and the state of the planet. Jupiter's influence on water therefore contains the same duality seen elsewhere. A giant planet can separate reservoirs and mix them. It can eject bodies and deliver them. It can reduce one flux while raising another. The title asks whether Jupiter kept Earth alive. Before life existed, the more relevant question may have been whether Jupiter altered the ingredients available to a growing terrestrial world. The evidence supports influence. It does not support a single celestial delivery service. The present asteroid belt carries Jupiter's rhythm in empty places. The most familiar are the Kirkwood gaps, regions with fewer asteroids at orbital periods that form simple ratios with Jupiter's 12-year circuit. Daniel Kirkwood identified the pattern in the 19th century. Modern orbital catalogs show the gaps with far greater precision. At the 3-to-1 resonance, an asteroid completes 3 orbits for each orbit of Jupiter. The corresponding semi-major axis lies near 2.5 astronomical units. At the 2-to-1 resonance, near 3.27 astronomical units, the asteroid completes 2 circuits for Jupiter's 1. Other gaps occur at 5-to-2 and 7-to-3 ratios. A simple ratio does not mean Jupiter meets the asteroid in the same place and throws it out immediately. Resonant dynamics involve repeating gravitational geometry. Over many cycles, the asteroid's eccentricity can grow. Its orbit becomes more elongated, eventually crossing Mars or entering regions where terrestrial encounters become possible. The gap develops because bodies do not remain stable there for the age of the solar system. Some resonances contain stable objects rather than gaps. The outcome depends on which angle librates, how eccentric the orbit is, and how perturbations from Saturn and the terrestrial planets combine. Celestial mechanics uses the same small set of laws to produce apparently opposite structures. Mean motion resonance is not the only repeating influence. Secular resonances concern the slow precession of an orbit's orientation rather than the ratio of orbital periods. When an asteroid's precession frequency matches a planetary mode, eccentricity or inclination can change over long intervals. The inner belt's Nu 6 resonance, shaped strongly by Saturn within the full planetary system, is another important route toward near-Earth space. Jupiter is dominant, but never dynamically alone. The mass behind the pattern remains 318 Earth masses. Jupiter does not need to approach the asteroid belt physically. At its present average distance of 5.2 astronomical units, it imposes a tempo. Asteroids at certain orbital periods repeatedly receive its pull in a correlated way. Sunlight provides a slower entrance to the resonance. Small rotating asteroids re-radiate absorbed heat unevenly, producing the Yarkovsky effect. Over millions of years, that tiny thrust can move a body's semi-major axis. Collisions can also place fragments near unstable zones. Once a fragment reaches a strong resonance, gravitational evolution accelerates. This is one of the clearest ways Jupiter can contribute to hazard rather than simply reducing it. A resonance is a route from a long-lived main belt orbit toward near-Earth space. Jupiter also helps eject bodies after encounters, limiting how long some remain dangerous. The pathway includes both actions. A gap in the belt can become traffic in the inner system. Follow one hypothetical asteroid near the 3-to-1 resonance. It begins as a fragment from a collision in the middle belt. Its parent body may have orbited safely for billions of years. The new fragment is small enough for thermal recoil to matter. Its semi-major axis changes by a tiny amount each year. Eventually, the fragment enters the resonant zone. It completes 3 trips around the Sun during one Jovian year. Jupiter is not always on the same side at the same instant, but the relevant orbital angles repeat. Small perturbations no longer average away. The asteroid's eccentricity changes systematically. As the orbit elongates, perihelion moves inward. The asteroid can begin crossing Mars. A close encounter with Mars changes the orbit again. Later, it may cross Earth or Venus. The object's classification changes from main belt asteroid to near-Earth object, but its material has not changed. Only its path has. Population models do not trace every near-Earth object to one exact parent. They simulate flows from several source regions and compare the resulting distributions with surveys. Strong resonances with Jupiter, the secular resonance known as Ephe sits near the inner edge of the belt, and intermediate Mars-crossing populations all contribute. Cometary sources add a smaller but important component. Jupiter's influence in this chain is real, but not solitary. The Yarkovsky effect delivers small bodies to the resonances. Saturn helps shape secular dynamics. Mars, Earth, and Venus modify planet-crossing orbits. Collisions create the fragments. Calling Jupiter the source would be as incomplete as calling it the shield. The timescale also changes the emotional meaning. A 3-to-1 rhythm repeated over millions of years is not a targeted throw. It is statistical transport through orbital phase space. Most fragments do not strike Earth. They may hit the Sun, collide with another planet, be ejected, or move onto other orbits. Impact probability belongs to a population, not a destiny attached to one stone. Still, the route demonstrates why the guardian metaphor cannot survive unchanged. Jupiter's distant pull helps open doors from the belt. The planet that clears a resonant gap does so by sending objects somewhere else. Empty space at 2.5 astronomical units is evidence of movement, not evidence that every displaced body became harmless. Near-Earth objects are defined by their orbits, not by an origin story. Most are asteroids. Some are extinct or active comets. Their paths bring perihelia within 1.3 astronomical units of the Sun, placing them in the broad neighborhood of Earth's orbit, even when no immediate collision is possible. Surveys discover and track these bodies. Orbit calculations estimate close approaches and uncertainties. Population models correct for what telescopes miss, because dark, small, or poorly placed objects are harder to detect. The resulting picture is a steady-state flow. Objects arrive from source regions, spend limited time on near-Earth orbits, and are removed by impacts, the Sun, ejection, or dynamical change. That operational work changes the practical meaning of protection. A distant planet cannot warn Earth about the object that remains after all gravitational sorting. Telescopes, repeated astrometry, radar when available, and numerical orbit propagation provide the warning. The orbit uncertainty narrows as observations accumulate. Deflection planning, if ever needed, begins from that measured path. Jupiter explains part of the population. Planetary defense addresses the individual object. Mikhail Gronvik and colleagues built a widely used debiased model from multiple source regions. The model connects observed near-Earth orbital distributions to escape routes from the main belt and to cometary populations. Jupiter appears in that structure through the resonances that help destabilize belt objects, but it is only one component of a network. This network explains why a lower number of asteroids in a resonance does not translate into zero hazard. Clearing a source region can create a transient flux. Once objects enter near Earth space, Jupiter may have little direct influence on a particular close approach. The terrestrial planets and the Sun dominate the local geometry. The scale of impact risk also depends on size. Small meteoroids enter Earth's atmosphere frequently and usually burn or fragment. Kilometer-scale asteroids are far rarer and carry global consequences. A model that changes the number of all impacts does not automatically change the number of civilization-scale impacts by the same fraction. That distinction matters when simulations count test particles striking an enlarged model Earth to obtain useful statistics. The particles represent a source population. They do not reproduce every physical breakup, thermal effect, collision, and observational bias. Results are comparative. One Jupiter configuration produces more or fewer modeled impacts than another. The current near-Earth population is therefore a measured and modeled traffic system. Jupiter helps shape some on-ramps and some exits. Planetary defense works in the inner lanes, where precise observation matters more than a distant story about a giant planet. Not every small body influenced by Jupiter is being cleared. Thousands of known Trojan asteroids share Jupiter's orbit around the Sun. They gather in two broad swarms near the L4 and L5 Lagrange regions, roughly 60 degrees ahead of and behind the planet. In a frame rotating with Jupiter, the combined gravity of the Sun and Jupiter creates stable zones around those points. Trojan asteroids do not sit motionless. They orbit the Sun while tracing looping paths around the equilibrium regions. Their stability can persist for immense spans of time. This population shows Jupiter as an organizer and storehouse. The planet's gravity protects the resonant relationship rather than emptying it. A body near the correct range of orbital elements can remain associated with the swarm. A body in another configuration may become unstable. The Trojans also preserve clues about migration. Their colors and compositions are diverse, and models of giant planet instability can capture objects into the swarms from a primordial planetesimal disk. If that occurred, the Trojans are samples from regions rearranged while Jupiter moved toward its present orbit. NASA's Lucy mission was designed to visit them. It launched on October 16, 2021, and uses an intricate sequence of Earth gravity assists. Its planned encounters include targets in the leading L4 swarm and later the binary Patroclus-Minoetia system in the trailing L5 swarm. The mission treats the Trojans as records of formation, not as stones Jupiter caught on the way to Earth. Stable storage has consequences for the shield question. Material parked in resonance is material not currently crossing Earth's orbit. Yet the Trojans are not a collection of intercepted impactors with known prior trajectories. Their existence does not tell us that they would otherwise have struck Earth. It tells us that Jupiter creates long-lived dynamical niches. The asteroid belt gaps and Trojan swarms sit in the same solar system. One is depleted at certain resonances. The other is populated at the 1-to-1 resonance. Jupiter's gravity can empty and fill. It can destabilize and preserve. The role depends on phase, the timing relationship among orbits. That is a more precise idea than protection. It is also more elegant. A planet 318 times Earth's mass writes its influence not only in impacts, but in the quiet geometry of bodies that avoid impacts for billions of years. Lucy carries cameras and spectrometers toward objects no spacecraft has visited before. The mission's path itself demonstrates orbital exchange. Earth flybys change the spacecraft's heliocentric velocity without requiring enough fuel to accelerate directly to Jupiter's distance. Later geometry guides Lucy from the leading Trojan swarm back past Earth and onward to the trailing swarm. The target list contains variety. Eurybates is associated with the collisional family and has a small satellite named Keta. Polymele also has a satellite. Lucas rotates slowly. Oris offers another surface and composition. Patroclus and Menoetius form a near-equal binary, two bodies orbiting their common center while sharing Jupiter's larger path. No single target represents all Trojans. A collisional fragment can expose interior material unlike an undisturbed surface. A binary preserves information about capture and gentle survival that a disrupted family records differently. Comparing several bodies gives the mission leverage. Patterns shared across the swarms may reflect origin, while differences may record later local histories. Their differences matter because the Trojan swarms may contain objects captured from multiple parts of the primordial outer disk. Surface colors, densities, crater histories, and satellite systems can test models of where the bodies formed and how they were transported. The observations will not replay migration, but they can eliminate stories that predict the wrong materials. This is how scientists approach an ancient counterfactual. No single crater or color answers whether Earth needed Jupiter. Multiple records constrain the allowed histories. Meteorite isotopes constrain early separation. Mars's low mass constrains the terrestrial disk. Asteroid compositions constrain mixing. Trojan properties constrain capture during migration. The evidence is distributed because the event was distributed. Planet formation did not leave one archive. It left many populations, each altered by later collisions and radiation. A successful model must connect them without claiming more precision than the records allow. Lucy also reminds us that the present solar system is still being explored. Before the mission reaches its first Trojan swarm, many statements about those bodies remain based on remote spectra and light curves. New close observations can change formation inferences while leaving basic orbital mechanics intact. For the title, the Trojans contribute a modest but important lesson. Jupiter's influence cannot be counted only by objects that hit planets or escape. Long-term storage changes the available traffic too. A body kept in a stable swarm is removed from other pathways for as long as that stability lasts. But storage is not rescue. The Trojans lead and follow Jupiter because of resonance, not because the planet evaluated a threat to Earth. The old map is gravitational, indifferent, and remarkably structured. Beyond Jupiter and inside Neptune lies a population called the Centaurs. Their orbits cross or approach those of the giant planets, making them unstable over solar system timescales. Many began farther out in the scattered disk beyond Neptune. Encounters moved them inward one planetary neighborhood at a time. The name reflects their mixed appearance. Centaurs can behave like asteroids, yet some develop cometary comae and tails as volatile material becomes active. Their physical identity is icy. Their dynamical identity is transitional. They are travelers moving through a sequence of gravitational encounters. Their surface colors range broadly, suggesting different compositions or histories of irradiation and activity. Some possess rings or satellites. These physical details matter because dynamical labels can hide diversity. Two objects on similar unstable orbits may respond differently to heating, fragment at different stages, and survive different numbers of perihelion passages. A purely gravitational calculation follows their path cleanly, while the real bodies are changing along those paths. Neptune often begins the handoff. A scattered disk body reaches a Neptune crossing orbit. Encounters can reduce its perihelion and pass it toward Uranus. Uranus can pass it toward Saturn, and Saturn toward Jupiter. Not every object follows a neat chain, but the broad pathway brings outer material into the realm of the largest planet. Once a centaur becomes Jupiter crossing, its orbit can change rapidly. A close encounter may reduce its orbital period and create a Jupiter family comet. Another encounter may send it back outward. The object can strike a planet or the sun, fragment, become dormant, or escape the solar system. This is an active supply line. Jupiter does not create the scattered disk, but it controls the final stages for many objects entering short-period comet orbits. The phrase Jupiter family describes that dynamical control. It does not mean the comet formed beside Jupiter. For Earth, the supply line creates a paradox. Only if the planet is assumed to have one job. Jupiter can inject centaur-derived comets into the inner solar system, increasing opportunities for terrestrial encounters. Because Jupiter is massive, it can also eject them efficiently, reducing their residence time. More bodies may enter, yet each may remain for fewer returns. Impact flux depends on both supply and lifetime. A smaller giant might inject less effectively, but retain objects longer. A larger giant might inject and eject on different schedules. The maximum hazard need not occur at the maximum planetary mass. The Centaurs make this relationship visible in slow motion. They are not a fixed cloud approaching a gate. They are a changing population carried through a set of planetary relays. Jupiter is the last powerful relay before the inner system, and a relay can send traffic in either direction. Jupiter family comets usually have orbital periods shorter than about 20 years and low to moderate inclinations. Their dynamics are strongly influenced by Jupiter, often summarized with a quantity called the Tisserand parameter. The parameter is not perfectly conserved during close encounters, but it helps distinguish broad comet populations. Most Jupiter family comets are modeled as descendants of trans-Neptunian objects from the scattered disk. They move inward through the Centaur region. Repeated encounters shorten their periods until they visit the inner solar system, often enough for sunlight to drive visible activity. Comet 67P Churyumov-Gerasimenko, visited by the European Space Agency's Rosetta mission, belongs to this family. Comet 9P Tempel 1, struck by NASA's Deep Impact Probe in 2005, does too. Their present orbits are temporary stages, not birth locations. Each perihelion passage changes a comet physically. Sunlight warms volatile ice. Gas carries dust away and creates a coma and tails. Jets alter rotation and can nudge the orbit. Nuclei split or become dormant. Dynamical simulations that treat comets as indestructible test particles therefore capture only part of their lifetimes. Jupiter changes the orbital part. A close approach can lower perihelion so that a comet crosses Earth's orbital distance. It can raise perihelion and reduce the immediate hazard. It can alter inclination, shorten or lengthen the period, or eject the comet entirely. Successive returns provide successive chances for change. The family name has encouraged the idea that Jupiter owns and controls these objects in a protective sense. The more accurate meaning is that their orbital histories cannot be understood without Jupiter. The planet is the dominant scatterer in their current region. That dominance can raise Earth's modeled impact flux compared with a system containing no giant planet. In the Horner and Jones Centaur experiments, the presence of a Jupiter-like body supplied objects to Earth-crossing orbits while also removing them. Intermediate masses sometimes produced a larger flux because they were capable injectors, but less efficient ejectors. The lesson is not that Jupiter is Earth's enemy. It is that short-period comet traffic is generated by the same interactions that eventually clear it. Entry and exit belong to one process. Consider a comet approaching Jupiter while traveling inward from Saturn's region. Relative position determines the result. If the comet passes on one side of the moving planet, it can lose heliocentric energy. Its semi-major axis shrinks. Its orbital period shortens. Perihelion may move deeper into the inner solar system. The new orbit can cross Mars and approach Earth. Sunlight activates the surface. Astronomers detect a coma, calculate the path, and classify the object as a Jupiter family comet. The planet has not aimed it at Earth. It has changed a broad set of orbital elements, one combination among many that allows inter-system passage. Repeated encounters can refine the path. A comet may return near Jupiter after several revolutions because its period remains commensurate with the planet's. Another deflection can move it away from Earth or closer. Chaos grows because a tiny difference in the first encounter changes the timing and distance of the next. This sensitivity limits long-term predictions for many comets. Astronomers can calculate near-term motion precisely, but thousands of years of repeated planetary encounters produce branching possibilities. Physical outgassing adds further small forces. Beyond a certain horizon, impact probabilities belong to statistical populations rather than one deterministic forecast. Jupiter's inward handoff has constructive implications too. Comets and primitive asteroids carry volatile compounds and organic molecules. Early impacts contributed material to terrestrial planets. The amount retained depends on speed, angle, atmosphere, and planetary state. Delivery and destruction are not separate categories written on the incoming body. In the present era, a newly injected comet is a hazard to track. In the formation era, similar transport may have contributed ingredients. The biological interpretation changes with time, even when the orbital mechanism is similar. This is why the title cannot be answered by counting only ejections. A planet that removes comets may first create the population whose members enter the inner system. A model with no Jupiter can have fewer Jupiter family comets precisely because there is no Jupiter to form that dynamical family. The shield disappears when the baseline changes. Fewer removals do not necessarily mean more impacts if fewer bodies are injected. The complete accounting must follow objects from their source through the handoff to their final removal. Now follow the opposite geometry. A comet approaches Jupiter in a way that lets it gain heliocentric energy. The planet transfers a minute fraction of its orbital momentum. The comet leaves on a larger orbit. If the energy gain is sufficient, the new path is hyperbolic and the object escapes the sun entirely. Jupiter is exceptionally effective at this because it combines 318 Earth masses with a relatively close orbit around the sun. It moves fast enough to provide a substantial gravitational assist and has a large encounter cross-section. Saturn also ejects objects, but Jupiter dominates many routes from the inner and middle solar system. Ejection cleans the traffic permanently. An object on an unbound path will not return after another orbital period. Over billions of years, this process helped remove a vast amount of leftover planetesimal material. It also helped populate interstellar space with bodies cast out from the solar system. The same mechanism can capture in rare circumstances if energy is lost through a suitable multi-body interaction. Comet Shoemaker-Levy 9 became temporarily bound to Jupiter before its final collision. Irregular moons may record captures assisted by additional interactions or collisions during the early system. Pure two-body gravity cannot permanently capture an object without some way to remove energy. For impact studies, ejection rate controls residence time. A population supplied steadily to Jupiter crossing orbits reaches a balance between new arrivals and removals. Increased Jupiter's mass and ejection can become faster, but injection efficiency may change too. The resulting Earth impact rate is the product of several competing effects. This explains why some experiments find an intermediate mass giant produces more impacts than full Jupiter. A smaller planet can perturb bodies into Earth crossing paths, but may take longer to eject them. The bodies remain available for more returns. At still lower masses, injection itself weakens and the impact flux can fall again. There is no smooth scale labeled more Jupiter, more safety. Different populations respond differently. Orbital eccentricity and inclination alter the relationship further. Ejection is the action that most resembles shielding because it removes a potential impactor from every future Earth encounter. Yet even here, the key word is potential. The escaped object had many alternate paths. Science can count how a modeled population changes. It cannot say each ejected comet was headed for Earth. Long-period comets begin from a different reservoir. The Oort cloud is inferred to surround the solar system at immense distances, perhaps extending tens of thousands of astronomical units from the Sun. Passing stars and the tidal field of the Milky Way can disturb objects there and send some inward on nearly parabolic orbits. These comets arrive with periods measured in thousands or millions of years, or on their first recorded passage. Their inclinations are broadly distributed. They can enter from far above or below the plane in which the planets orbit. Many cross Jupiter's distance once on the way toward the Sun and once on the way out. Their near parabolic speed makes each planetary encounter consequential. A small change in energy can turn an extremely long-bound orbit into an escape path or shorten the period enough for a future return. The comet may be active only during a tiny fraction of its immense orbit. For most of its history, it remains a dark nucleus in cold outer space, beyond direct observation and vulnerable to distant stellar and galactic perturbations. For this population, Jupiter behaves more clearly like a remover. Horner, Jones, and Chambers simulated Oort cloud comets with giant planets of different masses in Jupiter's orbit. Their modeled Earth impact flux was highest when no giant planet was present and generally fell as the giant's mass increased. The reason lies in the incoming supply. Galactic tides and stellar perturbations inject the comets regardless of Jupiter. The giant planet does not need to create the family. It can eject incoming bodies after one or several passages, reducing the number that return and the time they spend in hazardous orbits. The result supports a real shielding effect, but only for this source population within the assumptions of the simulations. Long-period comets are not the dominant source of known near-Earth object risk. Their high speeds and limited warning time make them important, yet their flux is much lower than that of asteroids. Jupiter can also perturb a long-period comet onto a shorter orbit or redirect one inward. Individual exceptions remain. The statistical result says the population produces fewer modeled Earth impacts with a massive giant at Jupiter's location than without one. This is the strongest version of the Guardian story, narrowed until it becomes scientifically useful. Jupiter helps clear Oort cloud comets. It lowers a component of impact flux. It does not establish that Earth owes its existence to that reduction. The difference between a component and the whole will recur. Asteroids begin mostly inside Jupiter. Short-period comets are supplied through Jupiter's region. Long-period comets are supplied from far outside by other forces. Three source architectures produce three answers to the same planet. Short-period comets reverse the simple result because their source pathway depends on the giant planets. Remove Jupiter, and the modeled population is not merely cleared less efficiently, it is injected differently. The comparison changes both the drain and the faucet. In the Horner and Jones Centaur experiments, Test particles began on orbits representative of Centaurs. Systems with different Jupiter masses were integrated, and impacts on an enlarged model Earth were counted to build statistics. A full mass Jupiter did not act as a universal shield. In many cases, a giant planet increased the impact flux relative to no Jupiter. The peak could occur below one Jupiter mass. A sub-Jovian planet scattered objects inward effectively, but removed them less quickly. They remained on potentially Earth-crossing paths for more orbital returns. Full Jupiter ejected them more efficiently, reducing their residence time after injection. This result is sometimes summarized as Jupiter makes impacts worse. That is also too simple. The simulations compare specific starting populations, masses, and architectures. They do not reproduce every physical comet breakup or every early solar system condition. They reveal a mechanism and a non-monotonic relationship. The term non-monotonic is useful. It means the result does not consistently rise or fall as Jupiter's mass increases. Hazard can climb, reach a maximum, and fall. A 50 Earth mass or Saturn mass object may produce a different balance from a 318 Earth mass Jupiter. This matters beyond our solar system. A giant planet's presence cannot be used alone to declare an inner rocky planet protected. The giant's mass, orbit, eccentricity, inclination, neighboring planets, and small body reservoirs all influence the impact environment. Even the age of the system matters because reservoirs deplete. For Earth, the present Jupiter likely shortens the dynamical lifetime of many Jupiter family comets. It also helps make them Jupiter family comets. Both statements are true. The title asks for one direction of causation. The short period population supplies a loop. Outer bodies move inward through Neptune, Uranus, Saturn, and Jupiter. Jupiter completes the injection and later completes the removal. Counting only the ending makes it look like a shield. Counting only the beginning makes it look like a threat. Following the full loop shows a gatekeeper. Asteroids begin with another geometry. Their main reservoir lies inside Jupiter's orbit. The planet influences them primarily through resonances, rather than a chain of inward encounters from the outer system. Removing or changing Jupiter therefore reshapes the escape routes from the belt. Horner and Jones simulated test particles representing asteroids and varied the mass of a planet in Jupiter's orbit from 0 through fractions and multiples of Jupiter's mass. Their results challenged the universal shield idea. A giant planet could significantly enhance the modeled asteroidal impact rate on Earth. Again, intermediate masses were important. A planet large enough to stir the asteroid belt and drive bodies into resonances, but less efficient at rapidly ejecting Earth-crossing objects, could maintain a substantial impact flux. Full Jupiter altered and removed the population differently. The starting belt in a numerical experiment is a controlled representation, not an untouched copy of the real ancient belt. The real belt has already evolved for billions of years under Jupiter's actual influence. A no-Jupiter belt would not have the same mass, gaps, or source distribution. This prevents the experiment from becoming a literal replay of Earth's alternative history. What the experiment establishes is dynamical possibility. Jupiter can be a source of impactors from an inner reservoir. The result aligns with the observed resonant pathways that feed near-Earth objects. It also explains why the direction differs from the Oort cloud result. Location is decisive. For distant comets already injected inward, Jupiter often acts as a final remover. For asteroids stored inside its orbit, Jupiter can open escape routes whose inward branch enters terrestrial space. A planet cannot shield equally against populations on both sides when its gravity rearranges both. Earth's actual impact record combines these flows with local effects and changing source populations. The largest known biological consequences cannot be assigned to Jupiter merely from the impactor's broad category. A particular asteroid may have reached its path through a resonance shaped by Jupiter, while the probability of the exact collision depends on later encounters and timing. The asteroidal result shifts the answer again. Jupiter may lower one cometary flux, raise another cometary flux, and help supply asteroids. The word friend or foe becomes a false choice. The planet is a cause without being an agent. Changing Jupiter's mass is only one experiment. The real planet travels on a slightly eccentric orbit with a modest inclination relative to the solar system's reference plane. Alter those elements, and resonances move or strengthen. Encounter velocities change. The asteroid belt and comet pathways respond. In a later study, Horner and Jones varied the eccentricity and inclination of the Jupiter analog. Higher eccentricity generally increased the modeled asteroidal impact flux and also raised the short period comet flux to a lesser degree. A more elongated Jovian orbit sweeps a broader radial range and perturbs small bodies more strongly. Increasing inclination produced another effect. A highly tilted Jupiter strongly disturbed the asteroid belt. The initial impact flux could rise, but the belt could become depleted so quickly that little material remained for a long-term flux. A violent early clearing can lead to a quiet later system. This distinction between rate and integrated history is crucial. A planet can produce a brief bombardment followed by scarcity. Another configuration can sustain a lower flux for billions of years. Biological consequences depend on when life begins, how quickly it recovers, and which impact sizes occur during each interval. Saturn changes Jupiter's secular effects. Terrestrial planets contribute their own resonances. The initial mass and width of the asteroid belt determine how much material can be delivered. A giant planet cannot be evaluated apart from its system. Even the ordering of events can reverse an interpretation. A tilted giant may empty a belt early, creating a brief interval of strong bombardment and a later era with little remaining source material. Observers arriving late would experience the quiet system and might call the giant protective. The ancient crater record would preserve the earlier cost. A time average number would hide both phases. The phrase a Jupiter therefore hides many variables. It can mean one Jupiter mass, a 5.2 astronomical unit orbit, the real eccentricity, the real inclination, a Saturn companion, and the present small body reservoirs. Move any term and the answer changes. This is one reason exoplanet discoveries do not support a simple rule that systems with giant planets are safer. Giant planets have been found close to their stars on eccentric orbits and in resonant chains. Some systems host smaller planets too. Their impact histories and formation pathways differ from ours. The real Jupiter is not an interchangeable shield unit. Its role emerges from a particular orbit and a particular architecture. Earth may have benefited from parts of that arrangement and endured hazards created by other parts. The geometry is the explanation. The most vivid evidence of Jupiter intercepting a comet arrived in July 1994. Comet Shoemaker-Levy 9 had been discovered the previous year by Carolyn Shoemaker, Eugene Shoemaker, and David Levy. Images showed a remarkable chain of fragments rather than one intact nucleus. The comet had passed close enough to Jupiter for tidal forces to tear it apart. It was temporarily captured in a Jupiter-centered orbit and headed toward collision. Fragments were labeled with letters from A through W, with some letters representing pieces that were faint or uncertain. Beginning on the 16th of July, the fragments struck one after another over several days. The impacts occurred on the side of Jupiter initially turned away from Earth, but the planet's rapid rotation brought the dark scars into view. Telescopes on Earth and in space observed plumes and atmospheric disturbances. NASA's Galileo spacecraft, still traveling toward Jupiter, had a direct line of sight to the impact sites. Some scars grew larger than Earth. The comparison describes the spread of dark atmospheric material, not the solid size of each fragment. Energy deposited deep in the atmosphere lofted material upward and changed Jupiter's chemistry and temperature locally. The event became the first collision between two solar system bodies, predicted and watched in such detail. Shoemaker-Levy 9 appears to offer a perfect guardian image. A comet meets Jupiter and disappears into the giant atmosphere instead of continuing through space. The collision is real. The alternative path is not. The comet was already bound to Jupiter after earlier encounters. Its orbit was shaped by the planet that eventually destroyed it. Without Jupiter, there would be no identical Shoemaker-Levy 9 trajectory waiting to continue toward Earth. The object might have remained farther out, encountered another planet, struck the Sun, or followed an orbit that never approached Earth. The event proves Jupiter captures and absorbs some objects. It demonstrates the immense focusing power of the planet and shows that impacts continue in the present solar system. It does not supply the missing counterfactual. The collision also placed a scale marker inside human memory. Astronomers did not infer the sequence only from ancient scars. They predicted fragment arrival times, prepared instruments, and watched the atmosphere respond. The success confirmed that orbital calculations could connect discovery, tidal disruption, and impact. What it confirmed was the forecast for a known object in the real system, not the broader claim that the event represented a diverted Earth impact. July 1994 gave astronomy a direct view of one endpoint. The marks in Jupiter's clouds were evidence of collision, not a receipt for a saved Earth. Counterfactuals become tempting when an impact is visible. If Jupiter was struck, it is easy to imagine the comet continuing inward along the same line if the planet had not been there. Orbital mechanics does not permit that simple subtraction. Jupiter's gravity shaped the approach long before the final contact. The planet changes the velocity of an object throughout the encounter. Remove the mass and the earlier path changes. Move the planet slightly and the timing changes. A comet that collides with Jupiter is selected from trajectories focused toward Jupiter by its gravity as well as trajectories that would intersect the planet's physical cross-section. This is called gravitational focusing. A massive body's gravity bends nearby paths inward, increasing the effective collision cross-section beyond the simple area of its disk. Jupiter is struck more often than a powerless sphere of the same radius would be. Some observed impacts are therefore caused in part by the same gravitational attraction that receives them. Earth has gravitational focusing too, though much weaker. The Sun focuses objects on a larger scale. Counting craters requires accounting for the target's ability to draw in passing bodies. A hit is not always an interception of a pre-existing straight path. Shoemaker-Levy 9 adds temporary capture. The comet's pieces had orbited Jupiter before impact. The event cannot be described as a last-second block at the outer edge of the solar system. It was a Jovian system event created inside Jupiter's gravitational domain. This does not reduce its scientific importance. The impacts revealed atmospheric waves, chemistry, and plume behavior. They demonstrated that large collisions are not only ancient. They encouraged systematic monitoring of Jupiter, which later found additional impact scars and flashes. But the title requires a population-level comparison. How many objects enter Earth-crossing paths with Jupiter present? How many are removed? How long they remain? And how those numbers change without the planet? One spectacular collision cannot answer those questions. The unseen trajectory deserves the same discipline as the visible scar. It is not known. The honest description ends where observation ends. Jupiter received the fragments. Earth was not involved. The rest belongs to simulation, and a simulation must rebuild the whole gravitational history rather than erase one circle from the final frame. The small bodies discussed so far can now be arranged by source. Asteroids begin mainly in the belt inside Jupiter. Jupiter family comets begin mainly beyond Neptune and move inward through the giant planet region. Long-period comets arrive from the distant Oort cloud under perturbations that begin far beyond the planets. For asteroids, Jupiter's resonances create routes out of a reservoir that otherwise might remain more stable. This can raise the terrestrial impact flux. Jupiter also ejects some evolved objects and help deplete the original belt, limiting the reservoir available today. For Jupiter family comets, Jupiter is part of the injection mechanism and a strong removal mechanism. The balance between those actions changes with planetary mass. Intermediate giant masses can retain injected objects longer than full Jupiter. For Oort cloud comets, the supply is less dependent on Jupiter. Galactic tides and passing stars initiate the inward fall. Jupiter then removes many visitors, and simulations show a clearer reduction in Earth impacts as the giant's mass increases. These are not contradictory studies. They ask about different rivers. A dam placed downstream can reduce one flow, while a channel cut upstream increases another. The physical analogy remains imperfect, but it captures why a global label fails. The relative importance of the reservoirs changes over time. The early asteroid belt contained more mass. Giant planet migration destabilized primordial populations. Late in solar system history, many reservoirs are depleted. Present impact risk is dominated by objects already in or near the inner system, not by a constant rain identical to the formation era. Object size distributions differ too. Comets can arrive faster than typical asteroids because of their eccentric or inclined orbits. Impact energy scales with mass and the square of velocity. A smaller, faster body can carry more energy than size alone suggests. Atmospheric entry and composition influence what reaches the ground. A complete statement about Jupiter would weight source flux, size, speed, residence time, and epoch. No single study includes every term with perfect certainty. The three-reservoir view provides the calmest answer. Jupiter's effect is conditional. State the source, the time, and the orbit, and the role becomes clearer. Remove those details, and the word shield becomes a story detached from its evidence. The next distinction concerns consequence. A world with more impacts is not automatically lifeless, and a world with fewer impacts is not automatically habitable. Planetary formation is made of collisions. Water and carbon-bearing material can be delivered by impactors. Large collisions can also melt surfaces, remove atmospheres, or trigger mass extinctions. Timing determines which interpretation applies. Before Earth had a stable crust, impacts were part of assembly. After oceans and early life emerged, the same energy could disrupt ecosystems. Later still, an extinction can erase lineages while opening ecological space for survivors. Biology does not assign one sign to impact. Frequency matters with recovery time. A single large impact may be survivable for microbial life sheltered underground or in the ocean. Repeated sterilizing events at short intervals would be different. Smaller impacts may affect regions without changing the global biosphere. The size distribution matters more than a raw count. Jupiter studies often use impact counts as a dynamical proxy. That is appropriate for comparing configurations. Translating the count into the probability of complex life requires additional assumptions about impact energy, atmosphere, ocean, geology, and biological resilience. Recovery is not uniform across the tree of life. Organisms in surface ecosystems face different pressures from organisms in deep rock, hydrothermal systems, or sediments. Dust and aerosols affect climate, while ejecta can ignite, bury, or chemically alter habitats. The same physical impact produces uneven biological outcomes. Astrobiological claims therefore require more than an orbital count, no matter how carefully that count was calculated. The phrase Earth still exists raises the threshold even higher. No known historical impact came close to dispersing Earth as a planet. The collision associated with the moon's formation transformed Earth while leaving a larger body behind. Later impacts altered the surface and biosphere. They did not threaten the planet's gravitational existence. If still exists means complex life persists, the claim enters astrobiology. If it means the planet remains in orbit, almost no plausible present small body flux qualifies. If it means the particular evolutionary history leading to humans, then countless small differences beyond Jupiter become decisive. The title, therefore, uses a deliberately broad phrase and must receive a narrow answer. Jupiter shaped the impact environment. Some of that shaping likely reduced hazards, some created them. The link from those changes to Earth's continued existence cannot be isolated. This is not a failure of science. It is accurate scale. Orbital mechanics can be calculated with extraordinary precision. Biological counterfactuals across billions of years cannot. The honest boundary between them is part of the result. The Grand Tack concerns migration, while the gas disk remained. Another family of models addresses a later stage, after the gas dispersed and the giant planets interacted with a massive disk of leftover planetesimals. The original version was developed by researchers working in Nice, France, and became known as the NICE model. In the 2005 formulation by Clemenus Tsiganis and colleagues, Jupiter, Saturn, Uranus, and Neptune began in a more compact configuration, on nearly circular, nearly coplanar orbits. As they scattered planetesimals, the planets migrated. Jupiter moved slightly inward while the outer giants moved outward. The changing relationship between Jupiter and Saturn triggered an instability. Their orbital eccentricities grew. Uranus and Neptune experienced encounters and moved through the planetesimal disk. Vast numbers of small bodies were scattered. Some were implanted into stable populations. Many were ejected. The model reproduced important broad features of the giant planet's present eccentricities and inclinations. Related papers addressed Trojan capture and the structure of the Kuiper belt. Later versions changed the initial planetary chain and sometimes included an additional ice giant that was ultimately ejected. The connection to a specific late heavy bombardment of the moon has become less certain as lunar chronology and dynamical models improved. The instability itself may have occurred earlier than the original delayed scenario. This is another reason to describe NICE as a model family rather than a settled timeline. For Jupiter's role, the key point is that the present architecture may be the aftermath of large-scale scattering. The planet helped remove a primordial disk and may have ejected an entire giant planet in some successful calculations. The quiet orbits seen now can emerge from a violent transition. That transition would have sent material both inward and outward. Some bodies entered the terrestrial region. Others became Trojans, irregular satellites, scattered disk objects, or interstellar wanderers. Jupiter again acts as an architect and a source of bombardment, then as a cleaner of the debris it helped mobilize. Earth survived whatever instability occurred. Whether Jupiter made that survival more likely depends on the exact timing and path. The model explains architecture more directly than biology. The solar system feels stable because human history occupies a very short interval. Planetary positions repeat predictably. Eclipses can be calculated centuries ahead. Spacecraft navigate among planets using equations that work with remarkable precision. Over millions and billions of years, the system is more subtle. Planetary interactions produce chaotic behavior, meaning tiny differences in initial conditions eventually lead to large differences in detailed positions. Chaos does not mean planets wander randomly from orbit to orbit tomorrow. It means exact long-term phase predictions lose certainty. Long-term integrations can still test whether broad orbital ranges remain bounded. A system can be chaotic yet stable, with planetary phases becoming unpredictable while semi-major axes stay within safe limits. Conversely, a seemingly orderly resonance can slowly exchange eccentricity until orbits cross. Stability is a statement about allowed regions over time, not about the ability to forecast the exact location of every planet forever. The present giant planets nevertheless occupy a durable architecture. Jupiter and Saturn remain separated from destabilizing close encounters. Uranus and Neptune orbit farther out. Most small bodies lie in belts and reservoirs whose unstable portions have been depleted over time. This mature stability may be an outcome of early instability. Planet scattering removes objects on dangerous or crossing orbits. Survivors occupy protected resonances or separated zones. A system looks ordered after the trajectories that violated the order have been cleared. Jupiter's large mass accelerates that sorting. It ejects planetesimals efficiently and opens gaps. It also exchanges angular momentum with the other planets. In models with an extra ice giant, a close encounter with Jupiter can expel the smaller planet while shifting Jupiter's orbit in a jump. That rapid change can help preserve the terrestrial planets from slower resonance sweeping. These scenarios remain constrained reconstructions. Their success is measured by how well they reproduce present orbital spacing, eccentricities, inclinations, Trojan populations, and the outer small body disk. No one configuration is guaranteed to be the exact history. Yet the concept provides another answer to the shield question. A planet can protect long-term stability by making an early system more unstable, clearing incompatible orbits quickly. It can also threaten the inner planets during that process. Outcome depends on sequence. Earth's calm present orbit is not evidence that every past influence was calm. The planet carries scars of accretion and impact. Jupiter carries its own scars. The space between them has been emptied by a history of exchanges. Stability is therefore not the absence of disturbance. It is the surviving pattern after disturbance. Jupiter helped create that pattern, but the path was not a continuous act of defense. The counterfactual can now be stated more carefully. Remove Jupiter at the present moment, and most planets would continue orbiting the Sun, though long-term resonances and small body traffic would change. Remove Jupiter before formation, and almost every initial condition relevant to Earth changes with it. There would be no 318 Earth mass core separating meteorite reservoirs. Gas and solids could move across the disk differently. Saturn might form at another rate or migrate along another path. The asteroid region could retain more mass, form planetary embryos, or be cleared by different mechanisms. Water-bearing material would follow other routes. Earth's embryo would accrete from a changed population. Its mass and orbit could differ. Mars might become larger. Additional planets might form between Mars and Saturn. A different set of giant planets could destabilize the inner system later, or a broadly Earth-like world might still emerge through another sequence. Simulations cannot hold everything constant because Jupiter was part of the process that set the conditions. Researchers can begin with identical disks and vary one giant planet to isolate a mechanism, but the resulting systems diverge. The comparison reveals sensitivity, not a photographic alternative. This is the deepest flaw in saying Jupiter saved a predetermined Earth. There was no predetermined Earth waiting behind the asteroid belt. The planet itself was an outcome of the same disk Jupiter altered. Change the disk's giant planet and the identity of the resulting terrestrial world changes. The point does not make Jupiter unimportant. It makes the influence more profound. A shield leaves the protected object essentially unchanged. An architect changes what the object becomes. Jupiter may have influenced Earth's building material, water access, impact environment, and neighboring planets before it ever removed a particular comet. There is also selection in the question. We ask from a world that survived. Any planetary system with observers has already passed through whatever formation and impact history allowed those observers. That does not mean the history was optimal or designed. It means only that the present is conditioned on its own past. Removing Jupiter from the beginning does not reveal a dead Earth. It reveals a different experiment whose endpoint cannot be named in advance. A no-Jupiter simulation might produce several outcomes. More material could remain in the asteroid region and form a planet. The terrestrial planets could acquire different masses and eccentricities. Saturn or another giant could dominate comet scattering. A water-rich Earth analog could form closer to or farther from one astronomical unit. Some systems might be less stable. Others might be stable in a different configuration. A giant planet is not required by physics for every habitable terrestrial planet, and its presence is not sufficient. Exoplanet discoveries show enormous diversity. Compact systems of rocky planets, giant planets close to their stars, eccentric giants, resonant chains, and architectures with wide gaps. Observations of other systems remain incomplete. Small planets far from their stars are harder to detect. Long orbital periods require years of monitoring. An apparent system without a Jupiter analog may contain one below current sensitivity. Population comparisons must account for those biases. Even so, the diversity makes one point secure. Nature can assemble planets through many pathways. Our solar system is not a universal template. Jupiter's role here may be specific to the masses, distances, and reservoirs that happen to form around the sun. If another Earth-like world forms without an outer giant, it does not disprove Jupiter's importance to our Earth. If a system with a Jupiter analog lacks terrestrial planets, it does not prove the giant destroyed them. Formation is a coupled process with many variables. The word reason in the title implies necessity. To establish necessity, every viable history without Jupiter would need to lack an enduring Earth-like world. No model or observation can support that universal statement. The available work supports contingency. Our planet's detailed history depended on Jupiter among many other causes. Contingency is not weakness. A river's path can depend on one ridge without that ridge being the only reason water reaches the sea. Change the ridge and another channel may form. The destination may shift or disappear. The result cannot be reduced to protection. Earth without Jupiter might be absent. It might be more massive, less massive, wetter, drier, closer to the sun, or accompanied by another planet. It might support life with another history. The honest answer is not one shadow world. It is a field of possibilities. After removing the simple shield, a strong conclusion remains. Jupiter shaped the solar system in which Earth formed and continues to shape the small body traffic around it. The evidence for influence is abundant, even when necessity cannot be proved. Jupiter formed early enough to affect the distribution of gas and solids. Meteorite isotopes record separated reservoirs during the first several million years. Models connect a growing Jupiter with that division, though some mixing persisted across it. Jupiter's migration is less certain in detail, but present orbital architecture and small body populations require substantial early evolution. The Grand Tack provides one route to a small Mars, a depleted mixed asteroid belt, and inward delivery of primitive material. Nice family models provide routes from a compact giant planet system to the current outer architecture. In the present belt, Jupiter's resonances are measured. The 3-to-1 and 2-to-1 Kirkwood gaps are visible in orbital distributions. Those resonances can raise asteroid eccentricities and feed planet-crossing pathways. Stable resonances preserve other populations, including Trojans and Hildas. The measured present and the reconstructed past support each other without becoming identical. Resonances observed today prove that Jupiter structures small body orbits. They do not prove the exact migration that placed every body there. Meteorite ages prove early chemical separation. They do not give Jupiter's longitude in the disk. Good reconstruction respects those boundaries while asking one model to explain as many independent records as possible. In the comet reservoirs, the source-dependent effects are supported by numerical experiments. Jupiter helps inject and remove short-period comets. It more clearly reduces the modeled impact flux from Oort cloud comets. Mass, eccentricity, and inclination alter every balance. Observed events confirm the mechanisms without answering the full counterfactual. Shoemaker-Levy 9 was captured, torn apart, and absorbed. Spacecraft use the same exchange of orbital energy in controlled gravity assists. Lucy travels toward bodies stored by resonance. Near-Earth object models trace flows through routes shaped by giant planets. These facts justify three descriptions. Jupiter is an architect because it helped determine large-scale structure. It is a gatekeeper because it redirects traffic between reservoirs. It is an ejector because its mass removes bodies efficiently. None of those descriptions requires intention. None makes Jupiter entirely beneficial. Architecture can exclude as well as build. A gate can open inward and outward. Ejection can follow injection. The evidence therefore supports a richer claim than the title's familiar story. Earth belongs to a system deeply marked by Jupiter. Our planet's exact formation and later impact history cannot be separated from that influence. What cannot be added is the word only, or the certainty that no enduring Earth-like world was possible without it. Science cannot identify every object Jupiter prevented from striking Earth. Once a body is deflected or ejected, its no-Jupiter trajectory is not preserved in nature. Simulations can estimate population differences, but an individual escaped comet does not carry a label naming the planet it would otherwise have hit. Science also cannot assign a single impact rate to Jupiter for all time. The asteroid belt has depleted. Comet reservoirs evolve. Planetary orbits migrate. The early bombardment environment differed from the present one. A configuration that produces a high initial flux may produce a low later flux after clearing its source. No model can hold Earth biologically identical while changing billions of years of impacts. Move one large collision and evolutionary history branches. Alter water delivery and atmosphere formation branches earlier. The specific organisms that eventually ask the title question are among the most sensitive outcomes. The Grand Tack cannot be presented as observed fact. It is a successful model with uncertain disk physics and alternatives. The timing and details of the giant planet instability remain debated. Meteorite chronologies constrain early separation without revealing every orbital step. The impact simulations cannot be read as exact forecasts for a no-Jupiter solar system. Their test particle populations and controlled starting conditions isolate mechanisms. A real alternate belt and comet reservoir would develop differently from the start. And the word exists cannot be allowed to drift between meanings. Jupiter may have influenced whether an Earth mass planet formed here. It may have affected the survival of atmospheres and organisms. It did not repeatedly prevent the physical destruction of an otherwise finished Earth in any documented way. These limits are not footnotes placed after a stronger claim. They determine the claim. Jupiter reduced some risks and raised others. It influenced formation without dictating a unique endpoint. It helped create a stable, mature architecture through processes that included scattering and bombardment. The unsupported statement is that Jupiter is a universal bodyguard, whose absence would certainly leave Earth destroyed. The supported statement is that Earth grew and endured inside a dynamical history in which Jupiter was one of the largest causes. That difference may sound modest. It is actually the distance between a fable and a scientific explanation. We have talked about a planet with 318 Earth masses, moving around the Sun every 4,333 Earth days, powerful enough to exchange orbital energy with bodies that pass through its domain. We have talked about meteorite reservoirs separated in the first few million years, and the inference that Jupiter's core became substantial while the terrestrial planets were still assembling. We have talked about the Grand Tack, an inward and outward migration model that can truncate the inner disk, leave Mars small, mix the asteroid belt, and transport primitive material across old boundaries. We have talked about the Kirkwood gaps, where simple ratios with Jupiter create unstable routes, and the Trojan swarms, where another resonance preserves asteroids beside the giant for immense intervals. We have talked about Centaurs moving inward from the trans-Neptunian region, becoming Jupiter family comets through encounters that can open the inner solar system and later close it through ejection. We have talked about long-period comets arriving from the Oort cloud, a population for which a massive Jupiter produces the clearest shielding result by removing visitors whose initial injection began elsewhere. We have talked about asteroids and short-period comets, populations for which Jupiter can increase modeled Earth impacts, because the planet helps create the pathways as well as the exits. We have talked about Shoemaker-Levy 9, 21 visible fragments striking Jupiter in July 1994, and why a real collision does not reveal the alternative trajectory that never occurred. We have talked about the NICE model, in which the settled outer solar system emerges from migration, scattering, and instability rather than from planets born quietly in their final lanes. Together, these pieces replace one picture with another. Jupiter is not a stationary guard beyond the belt. It is a moving participant in a system of reservoirs. It stores objects at L4 and L5. It empties other resonances. It receives impacts. It creates short-period comet paths. It expels bodies toward interstellar space. The direction changes because the source changes. Objects beginning inside Jupiter respond differently from objects beginning far outside. The epoch changes because a young disk contains gas and building material, while the mature system contains depleted belts. The consequence changes because an early impact can deliver ingredients, and a later impact can erase ecosystems. The single word shield cannot carry all of that structure. It keeps one visible action and discards the rest. The assembled system needs three quieter words: architect, gatekeeper, ejector. The direct answer to the title is no, not in the simple and absolute sense. Jupiter is not proven to be the reason Earth still exists. No observation or simulation shows that every solar system without Jupiter loses its Earth, and no population study finds that Jupiter uniformly reduces every kind of impactor. The more precise answer is that Jupiter is one major reason our solar system has its particular architecture. Its early growth separated and mixed material. Its possible migrations helped shape the terrestrial disk and asteroid belt. Its present resonances and encounters continue to redirect small bodies. Particular is the important word. The measured Earth cannot be detached from the history that measured Jupiter helped create. Our asteroid belt, Mars, Trojan swarms, and comet families carry linked evidence of that history. Yet dependence of one outcome on a cause is not the same as universal necessity. Another system can reach another viable arrangement through another sequence. For long-period Oort cloud comets, Jupiter behaves substantially like a shield. A more massive giant efficiently ejects these visitors, and models find fewer Earth impacts than in systems without the giant. That is a genuine protective effect. For asteroids and short-period comets, the planet can produce the opposite statistical effect. It opens resonant routes from the belt and helps inject Centaurs into inter-system comet orbits. Full Jupiter later ejects many of those bodies, but the supply and removal cannot be separated. For planet formation, the answer is deeper and less certain. A Jupiter free disk is not our finished solar system with one object erased. It is another beginning. Earth might not form. An Earth-like planet might form differently. Another architecture might support another enduring biosphere. The models cannot select one inevitable result. So Jupiter deserves neither the uniform title of bodyguard nor the uniform title of threat. It is a gravitational gatekeeper. Gates admit and release. It is an architect. Architecture creates some spaces by removing material from others. It is an ejector. Ejection makes a mature system quieter after a turbulent youth. Earth still exists because a vast chain of conditions remained within survivable ranges. Solar stability, planetary mass, orbit, water, atmosphere, geology, impacts, and biological resilience. Jupiter belongs in that chain. It does not replace the chain. The honest conclusion preserves the wonder without claiming certainty. Our world was not simply hidden behind a giant. It was formed inside the giant's influence. That influence continues without guaranteeing safety. Near-Earth surveys remain necessary. Future comets will still cross the planetary region. Resonances will keep moving fragments out of the belt, while Jupiter keeps ejecting other bodies beyond the sun. The system has no final state in which the traffic ends. It has only a mature, depleted set of reservoirs, evolving more slowly than before. From Earth, Jupiter looks almost still. Night after night, it moves slowly against the stars. Through binoculars, the 4 Galilean moons shift position. Through a telescope, cloud bands cross a disk whose light has traveled tens of minutes from the sun and then back toward us. Nothing in that view reveals the planet's long reach. The asteroid at 2.5 astronomical units does not display the resonance carrying it away from the 3-to-1 gap. The comet arriving from the scattered disk does not show the encounters that handed it inward from Neptune to Jupiter. The meteorite in a laboratory does not contain a map of the gas disk, only isotopic evidence that reservoirs stayed apart. Science builds the map from these partial records: a histogram of asteroid orbits, a chain of comet fragments, ratios measured in meteorites, the mass of Mars, the placement of Trojans, the eccentricities of giant planets. Each piece limits the possible history. The method depends on convergence. One model may reproduce Mars while leaving the asteroid belt too orderly. Another may capture Trojans while disturbing the terrestrial planets too strongly. Researchers compare failures as carefully as successes. The preferred history is not the most dramatic path. It is the path that survives the largest number of independent constraints with the fewest special adjustments. Even then, preference is not certainty. New asteroid surveys change population estimates. Sample return missions refine chemical links. Lucy will replace distant points of light with mapped worlds. Improved disk simulations may find routes not yet tested. A scientific history remains open to revision while its best supported mechanisms become increasingly clear. The resulting story is not one of shelter. It is one of exchange. Angular momentum moves from planetesimals to planets. Orbital energy moves from Jupiter to a comet. Water-bearing material crosses a chemical boundary. An asteroid leaves a belt and enters near Earth space. Another object leaves the sun forever. Earth is made from the consequences of exchange. Its iron sank inward while silicates formed a mantle. A giant collision helped create the moon. Volatile material arrived and escaped. The crust recycled. Life changed the atmosphere, and the atmosphere changed which life could continue. Jupiter's influence belongs to that broader history. It did not stand outside the process. It participated. The planet's enormous mass altered what remained, what moved, and what was lost. There is something more profound in that account than in the image of a guard. A guard preserves a finished thing. The solar system was never finished while its decisive events occurred. The worlds emerged together, coupled by gravity across distance and by material carried from one region to another. Earth is not the object behind the shield. Earth is one surviving expression of the same evolving system that made Jupiter. The giant beyond the belt is part of our origin without being the sole author of it, returned finally to the bright point beyond the asteroid belt. Jupiter has 318 Earth masses. It completes one orbit in 4,333 Earth days and one rotation in about 9.9 hours. Its cloud tops turn quickly. Its gravitational history unfolds slowly. Across the first million years, its core grew large enough to alter the disk. Across the next few million, it gathered more mass and may have migrated with Saturn. Across later ages, it helped scatter planetesimals, preserve Trojans, structure the asteroid belt, and clear bodies from unstable paths. The record is incomplete. The models remain plural. Grand Tack, nice. Alternate instabilities, different starting disks. Each is tested against the same surviving solar system, and none can restore every lost object or every vanished trajectory. That incompleteness leaves room for precision rather than speculation. A model can be rejected when it produces the wrong Mars, the wrong giant planet spacing, or an asteroid belt unlike the one observed. Another can remain plausible without becoming unique. The unknown history is not an empty page. It is a narrowing corridor bordered by measurements. Within that corridor, Jupiter appears repeatedly, not as a symbol, but as a mass in equations, not as a guardian, but as a source of resonances, encounters, migration, and exchange. The poetry comes after the mechanics, because the mechanics are already enough. What remains certain is the reach of the planet. Jupiter bends paths. Jupiter opens resonances. Jupiter ejects comets. Jupiter also sends bodies inward. The same gravity performs every action. That work continues quietly through every remaining age of the mature planetary system over time. So Earth does not owe its continued existence to a simple interception service at 5.2 astronomical units. It owes its particular history in part to a giant neighbor that changed the architecture before Earth was complete and continues to edit the traffic around it. That answer is less absolute than the old story. It is also closer to the universe as it is. Causes overlap. Effects change with time. Protection and danger can emerge from one law applied to different paths. No wall. No intention. No single rescued world. A disk divided. A belt shaped. Comets admitted and released. One planet influencing another across hundreds of millions of kilometers. Jupiter has 318 Earth masses. Earth is still here. Between those facts lies not one reason, but the long gravitational history of a solar system. Good night.